Hello, and again, I've come with my last minute.com, but it's the P1 required practicals. I have been really busy. Some of these PowerPoint slides, they take me several hours, but I try and make them really short when I do the video. So these are the required practicals. I'm doing them so that if you missed out on any of the practicals, or if you did not get to do some, or you've done them, you've forgotten, this is your chance to just refresh your memory. They might ask you to plan it, but from what we've seen so far, is talking about the practicals and applying them, judging by last year's GCSEs and the one we've already done. So it's really short. Let's go on to it. So the density one is the Eureka can practical. It's called the Eureka can because you need to use the Eureka can. When you have a regular shaped object, you can just measure the dimensions and then calculate the volume by multiplying the three sides you've measured, the length, the breadth, and the height. But if you have an irregular shaped object, you will need the Eureka can to get the volume in order to calculate the density, because with the mass, you can always measure the mass by using a balance. So this is for the regular object. So for the irregular object, you need to measure the mass on a balance. You feed the Eureka can to the sprout level. Then when you drop the object into it, water will be displaced. So you collect that water in the measuring cylinder. That becomes the volume. Once you know the volume, you've already know the mass. You can then use the formula density equals mass over volume, and to get your the density of the irregular shaped object. And on the next slide, I have an image to explain this further. It's quite an elaborate one, but I know that it kind of shows the basic thing that you need to know in the measuring with the Eureka can. So that should do it. It should help you remember what you did when you did the calculation or when you carried out this experiment in class. If you did not have the opportunity, well, this is it basically. The other practical is the IV characteristics. I being current and V or voltage. So it's to investigate what happens to the current passing through a component. For example, a lamp is a component. When the potential difference across it changes. The equipment you need as follows. This diagram explains how you should connect them. Just make sure you connect the ammeter in series and voltmeter in parallel. And then, to measure, obviously, the potential difference across the resistor, as in this diagram below. On this slide, you have a step-by-step method for the experiment. If you need to, pause it and then use it to just look at the steps to remind yourself of what you needed to do in this practical. When you plot your values, you should get a graph like so. If you use a filament lamp instead of a resistor, you will give you a slightly different graph, because as voltage increases, the bulb gets hotter, so resistance increases. The graph would also be different if you use a diode instead of a lamp. In a diode, the current only flows in one direction. So you have a graph that looks like so. At this point, I thought I'll pop in a slide just to help you recall your electrical symbols. And then I thought a fuse. Some of you might have forgotten what it is. It's simple, but it could be a one marker. There you go. It's designed to allow several amps of current through before it melts or blows. But when it does melt, it protects the house wiring. The next one is the resistance of a wire. The aim is to determine the level of resistance of different lengths of wires. The thickness stays the same, but the length is changed in the practical. This could be used when one is trying to determine the best length of wire to put into a fuse that would be used in an electrical appliance such as hairdryer or shaver or the like. The independent variable is the length of the wire. Dependent is resistance in ohms, and the control variables are that list, all of those. And the experiment will be repeated 3 times so an average can be taken to increase accuracy. I thought I'll pop this diagram in here for you to remind yourself. So that meter rule is the length you're changing. Yeah, you're changing that length of the resistance wire as you go along. So you move the crocodile clip along to increase the length. Yeah. And then this is a step-by-step method of what you should do. And at the end, you should plot your graph of resistance against the length for the resistance of the wire. With the values you've obtained, you would plot and get a graph that looks like so. The specific heat capacity one is another required practical. Is the specific heat of a material is the amount of energy required to raise 1 kg of that material's temperature by 1 degree Celsius. There is this formula. I looked at this formula in the series of questions I put together. And so is the energy transferred is equal to mass times specific heat capacity, always written as a little c times the change in temperature. To investigate the specific heat of copper, you will need these materials and see the diagram on the next slide. I thought I'll pop a simplified diagram of the setup of that experiment here. Sometimes when students find certain drawings on their paper, it just throws them off balance. But if you know the particular experiment this is talking about, then you're much more relaxed. You know you can actually tackle the question. That's why I just popped these diagrams there. This is a step-by-step method to investigate the specific heat capacity of a material. Here we're talking about the copper block and how you should record your readings, the temperature change that you observe. The thermoinsulators one is for triple science only, but I thought I'd just pop it here. Even though I focus on foundation and the combined science, since it's a required practical, those writing the combined are not doing it, but that does not mean that the science cannot be implied, because I still carry out this experiment. As a matter of fact, we do this experiment from year 8 when we're doing temperature changes and all of that, or heat transfers. We can do this. So it's a very simple one. It's one that students actually love doing because they can clearly obtain results without much ado. So yeah, it's for triple only, but I thought I'll put it there. The triple students who are following my videos, there you go, you have it. It's your extra required practical. It's a simple one. They're just trying to see which material would be the best insulator. That is, would be best at keeping the heat in. These are the steps that you need to follow. Remember to use the same volume of water in each can or container. What you're changing is the type of material. By the way, in all of these practicals, make sure you clearly identify your independent variable, the one that you're changing. The dependent is the outcome or the one you're measuring, and then your constant is the one you're keeping the same all through the experiment. I thought I'll just pop here some random values to kind of give you a bit of idea what is possible. So if you're using 3 or 4 materials, there will be clear differences on which one keeps the heat in. the best. So if it started at 80 degrees Celsius, the one that dropped to only 78 has only, there's a temperature change of 2, which is quite little, 2 degrees Celsius. So that one has kept the heat in for much longer. So I popped here. I was going to write a conclusion, but for the fun of it, I thought, you know what? I'll give them a little assignment. Yes, there you go. That's your assignment. That's your homework. Yeah. So use the above values to write a sentence about the best insulating material of the three. Safe. Some of my students will say it's clear, isn't it? It's obvious, which it is, just for the fun of it. And I wish you the very best tomorrow. It's a really hectic schedule for me, but so some of these videos I do them like early hours of the morning, or sometimes I have to do them really late at night. For example, it's well past midnight now that I'm doing this video, and I try to make it really short so you can watch it over and over again. Although it takes me several hours, this one took me about 5 hours to put the PowerPoint together, to research, make sure I'm putting the right information, because I don't want to mislead anyone. I want, if anything, I want all the people that watch my videos to do well, get the right information. And when you pick up your paper, be confident, because we have actually looked at all the topics, all the topics. I emphasize all. I want to touch everything so that when you get in there, you're relaxed, because that atmosphere, that attitude of relaxation enables you to just go into the paper smoothly, and then it's a fly, really. You just literally whisk through it, and you're thinking, what has happened here? Some students are finding it quite easy. It's not because they're too easy. People say all sorts of things, but trust me, there are other people who are struggling. That is the truth. They don't know what's going on. But so if you're finding it easy, it's because you've put in the work, and you deserve to have the paper easy. And I wish you the very best. See you again in my next video, and God bless you.